All right, so let me do a recap of what we have done so far, right? So we're talking about the hydrogen emission spectrum, and we're saying that this spectrum, this experiment is what gives us the evidence for what we know today. That is the first piece of evidence that showed us that electrons in the atoms orbiting the nucleus in discrete energy levels or quantum levels, not in physical shells. And it shows that each element has specific energy levels or quantum levels, or they each had specific quantum levels that had specific energy values. So the electron has to have an energy that is equal to that, the energy of the quantum level, in order to orbit in that quantum level. So this spectrum was the first one that provided us with evidence that electrons cannot just exist randomly. It cannot be just be located in between or anywhere. It has to be in specific discrete energy levels, right? So what we're saying now is, how did this experiment prove that to us? That's where we are now. All right, let us see. So the spectrum also proved that electrons cannot exist between quantum levels. So I started giving you some background information to say electrons can be excited from a lower quantum level to a higher quantum level if it is supplied with the exact energy, which is equal to the energy gap between the two quantum levels. So if an excess energy is given to the electron, as I said earlier, the electron is not going to take it, because the electron only is thinking about that I don't want to miss, I don't want to overshoot and go past this energy level. I want to land exactly. It's like somebody was sending you to the moon, right? And they calculated how much energy or whatever it takes to get you on the moon. Now, if they give you too much more than that, the next thing you're going to overshoot and pass the moon and end up in space. So I think that's exactly how the electron is thinking, right? So it's like, all right, I need to get the exact energy or I'm not going to move from where I am, okay? So that's literally the position of the electron. So if you're at a higher energy level, you can emit energy and come back to a lower energy level, but you first have to calculate the difference. So you must know the energy of the level you're currently in, and you must also know the energy of the level that you're trying to go to, right? And then you calculate the difference, and then you say, all right, this is the amount I need to emit, or this is the amount I need to absorb, okay? So the energy that the electron can give off, it depends on how much energy it's going to give off, because the energy can sometimes come out as visible light, it can sometimes come out as ultraviolet light or as infrared light. So this is a hydrogen emission spectrum with 4 lines, and you have to know the lines: red, well, greenish, or some of them look blue, or they call it cyan, and this is more bluish, and then this is violet. And these colors were because the electron, each one of them, the electron was going from a higher energy level to a lower energy level. So then I did a little bit about the electromagnetic spectrum to say that this spectrum is a continuous range of forms of electromagnetic radiation arranged by wavelength, right? Frequency and energy. It starts off from the longest wavelength and lowest energy, and it goes to the shortest wavelength and highest energy. So this is the longest wavelength. Radio waves has the lowest frequency and the lowest energy. And as you go up along the spectrum, you see that the wavelength is getting shorter and shorter, and that the energy is getting higher and higher. So ultraviolet has more energy in it than visible. Visible has more energy than infrared, which has more energy than microwave. Now, for the electromagnetic spectrum, what they all have in common, while they're all on the same spectrum, is that they all travel at the speed of light, right? But they have, they all travel at the speed of light, but they have different frequencies, and they have different wavelengths. So we then said that based on what the electron wanted to do, or depending on the amount of energy that the electron gives off, we can calculate to see what wavelength of light that would correspond to, and then figure out what part of the spectrum the light is going to come from. because electrons can emit these three types of light. So if we therefore had this energy level here, if we were at energy level number 2, which has this energy, and we want to go down to number 1, the electron would have calculated the difference between the two of them, found the energy difference, and would seek to only emit this specific amount of energy or absorb if it was moving the opposite direction. So also, I did show you this clip. So let me just, because as I said, I want it to be cemented. Let me just recopy. I believe it was.
This is one of our funnest demonstrations to show atomic spectra. I'm going to show the spectrum of a...
Yes. I had shown you this video, right? And what he did first was that he just had a regular light bulb, and he was showing us that from the regular light bulb, light was being emitted, and that if you should put a prism in front of the regular light bulb, which can basically diffract the light and separate it into its various components, right? You can see that this light, even though the light looks white, it really has all the different colors of the rainbow in it. So every single shade of red, every single shade of yellow, every single shade of green, blue, all of those lights are in it, right? So that's what was shown there. But then he showed that this is a continuous spectrum versus when we took an element. So we would have different elements in these jars. So these jars would have different elements like neon and hydrogen in the gaseous form. So he puts it inside this chamber and adds electrical energy to it. And the next thing you notice that it starts glowing and starts giving off light. So then he was interested to analyze this light. So when he puts the prism, he sees that, okay, I'm not seeing all the colors of the rainbow anymore. I'm only seeing specific colors now, right? So then that suggests that this is different from what he saw a while ago with the white light, with the regular bulb. So then this is hydrogen now. So he puts the hydrogen in the machine. As the electrical energy starts glowing, and here we are seeing 4 colors, the same 4 colors that we saw on the spectrum. And then he continued to do it with different elements. And every single element would give a different combination of colors. So then it led them, from this experiment now, it led them to actually have to really delve further into understanding what was happening. So now there was a discovery that was made right about the same time here, where they realized that energy could be broken down in terms of the wavelength of light, the frequency and the speed of light. So they had these 2 equations, E is equal to hc over lambda, energy is equal to Planck's constant times c over lambda, or energy is equal to Planck's constant times frequency. So frequency, basically c over lambda is the same thing as frequency. So they now understood that the wavelength you get would depend on the energy that was given off, and you could literally calculate it. So as we saw here, if the electron wanted to emit this amount of energy, it would use the equation, the Planck's constant would be put in, and it would calculate and solve for frequency to see what frequency that energy corresponded to, which was this. And when we check the electromagnetic spectrum, we see that this frequency would correspond to visible light. So it's somewhere in the visible region, but visible light has a lot of different colors with a lot of different wavelengths. So for us to know which specific color the electron will emit, we have to work out the wavelength, right? So then we were right here to say, based on what we saw he did in the experiment, we're like, no, trying to explain why did the hydrogen sample give off these 4 specific lines, the red at with a wavelength of 656, the cyan 486, the blue 434, and the violet 410. And we're going to explain why there are so many empty gaps. Why didn't we get any green light? Why didn't we get any yellow? So many other colors we didn't get. But then we look here and we see that when the red light was given off, That was when the electron was going from the number 3 to the number 2 level. And when it was the cyan, it was coming from number 4 to number 2. When it was blue, it was coming from number 5 to number 2. And the violet was from number 6 to number 2. So what we realized is that the greater the distance that the electron was traveling over, it was basically the shorter the wavelength of light that it gave off. And therefore the colors we saw. So this spectrum might seem very simple, but it does give a lot of information. Like the scientists were able to extract so much from this experiment. All right, go ahead with the question.
So miss, if hydrogen only has one, wait, oh, never mind.
Yeah, so even though a hydrogen only has one electron, guys, it doesn't mean that it doesn't have many energy levels, you know? So it has one electron, but it still has multiple quantum levels. But what really took place, which is what I'm going to give you now, I'm going to give you like the notes to now explain what the same video I just showed you, why did he like use the electrical energy to excite the electron, and then all of that is happening. So we're going to break that down now with the background of what we have learned so far. So let's explain just a moment how it was produced. All right. So the spectrum, so procedure. So I'm first going through the procedure, and then I'm going to explain how it gives evidence. All right, so first thing is that they had gaseous hydrogen. Was given electrical energy. Energy was absorbed and used to promote electrons to higher quantum levels. So the excited state, or actually the atom was unstable in this excited state. And thus the electron emitted energy to return to the n=2 level. So remember, there are trillions of hydrogen atoms in the sample. And each atom had its own transition being made. The energy emitted was equal to the difference between the source, the original just between the two quantum levels. type of radiation given depends on the wavelength, on the frequency that the emitted energy corresponds to. The light from the hydrogen sample was then passed to a prism. And produced a line spectrum of 4 colors of visible light. This is known as the Balmer series. So that's how the spectrum was produced. And then we're going to analyze the spectrum now. And we're done to analyze the results. Okay, I'll analyze the significance of this. All right, let's just analyze the spectrum. Well, I want to give you a different term. I was going to do analysis of the spectrum, but I just told you how we produce the spectrum, like the procedure. Then we're going to analyze it. Let's go ahead with the question.
Miss, why would the electron return to the n equals 2 level if it's a hydrogen atom? Won't it
Yeah.
return to
No, number 1, no, it didn't go back down to number. Some of them go to number 1, right? So we are really only interested in the ones that went to number 2. That's what we are discussing, because the ones that stopped at the number 2 level, those are the ones that gave off visible light, which we were able to see in the spectrum. The ones that went back to number 1, they gave off ultraviolet light, and we can't see the ultraviolet light. So that's why we basically just talk about the ones that stop at number 2 level.
But Miss, isn't it? But if it's hydrogen, why wouldn't it only be an n equal 1? Because it's hydrogen, or does it get extra electrons of electrical energy?
No, so not because it has 1 electron in them. Doesn't mean it has only 1 energy quantum level. I'm saying even though it has one electron on the first quantum level, it still has many other quantum levels inside the atom. It's just that at the ground state in nature, the electron is going to be at the first one, but the others are there still. So that is why when we were able to give the electron some energy and excite it, that's why it was able to go all the way up to those other energy levels and come back down. But it never came back down to the number one, or not, I shouldn't say it never came back. Some of them didn't come back down to the number one. Some of them stopped at number two, and the ones that stopped at number two gave off light. And that's what we were able to see with the prism.
But Mr. saying some of them, but is it one electrons or how is it multiple? I thought there was one electron.
Yeah, there's one electron, but because there are trillions of atoms of hydrogen in the sample, so every single atom is doing this. So some atoms, the electron is stopping at number two. Some of them are coming from number 3 to number 2. Some of them are coming from number 4 to number 2. So the reason why we're getting all of the different colors is because we had multiple. We had millions of atoms of hydrogen.
So
And
Miss,
we have one electron.
so Miss, if it came and then stopped at n equal 2, wouldn't that mean that it is still unstable?
No, it's not unstable. It's quite stable being at the number 2 level.
Okay, Miss.
So
Thank
what
you.
I'm saying here is that hydrogen has 1, right? So when we see the red light, some of the hydrogen atoms had the electron move from number 3 to number 2. Some of them, the electron move from number 4 to number 2. So this is not all happening in one atom, you know. That's the important thing for you to note. Each individual atom of hydrogen could only do one thing because they only have one electron. But because there are trillions of them, some of them were doing this, some of them were doing that, some of them were that. So when we get the light from the sample, we are seeing like the addition, like the summation of what everybody is doing. And so that's what we are seeing. But it's not that this happened in one individual hydrogen atom. One individual hydrogen atom could only do one specific transition. But together, we can get multiple transitions because there are millions of them.
Could you go back up to the steps for a second, please?
Okay.
So, thank you.
The lines of the spectrum represents represents an electron transition. From a higher quantum level to the n equal to some atoms, the electron moves from number 3 this energy and the energy emitted corresponds to red light. of wavelength. Atoms had conditions from n equal 4 to n equal 2. This produced I'm sorry, an emitted light cyan light. Of wavelength 486. The blue lights was for the condition from n equal 5 to n equal 2. And 434. Some atoms are transformed from 14, sorry, from n equal 6 to n equal 2. And gave violet lights of very 14. This series is called the Balmer series. Visible light. But I also want to notice that we want to observe some things that as the quantum levels get higher, I should say, note the following. As the quantum levels get higher, the gap between them narrows. This explains why the gap in the spectrum also narrows. Between lines of higher wavelengths. Between lines as we increase energy. And other thing too, the wider the gap, the greater the energy, and the shorter the wavelength of the lights. So then the final thing we have to know see is that how does this provide evidence for the fact that we have discrete quantum levels? So the next question must ask ourselves is how does this experiment so the hydrogen emission spectrum provides evidence for discrete energy levels because it consists of only specific distinct lines and not a continuous rate of colors. And each line represents a specific photon of energy and therefore wavelength that was emitted when an electron jumps from a higher energy level to a lower one. This means that only certain energy transitions and thus discrete energy levels are present. So they love asking this question. I'm going to expound on it also. Right. If it were a situation where there weren't specific or fixed energy levels, then you would have ended up getting a rainbow. If the energy values were not fixed, we would have obtained a continuous spectrum with all colors of light representing all possible transitions would have been made if there weren't specific energy levels inside. But whenever you have fixed or specific energy levels, you only will get a limited number of electron transitions and result in specific lines. And the blank spaces in the spectrum means that there were no transitions that were made that gave off that specific color of light, all right? All right, so I'm going to give you a chance to finish up this now and hope that you are convinced that this experiment did give evidence. And I want to tell you a little bit more about energy because you have been hearing me talking about the photon. I want you to understand what when we say that energy, a photon of energy. We want to make sure you understand because it's a new term that you're going to hear start to use. So let me give you a chance to copy that. So let me give you, 3 more minutes. So, the last thing I wanted to let you know about is the photon. So now we're going to talk about energy in terms of photons. So you're going to hear this term being used all the time. So let me just tell you what a photon is. Because I know I mentioned somewhere in my notes that the electron released a photon of energy. So a photon is an elementary particle of light, and not only light, but all forms of electromagnetic radiation is made up of photons. It's acting as a quantum of electromagnetic energy. Photons are fundamentally massless particles that travel at the speed of light. They exhibit wave-like and particle duality, meaning that they behave as both waves as well as packets of energy. I'm going to give you an image that kind of shows what we illustrate, what we mean a photon is. So we're basically saying that we have packets of energy moving in a wave-like manner. So they believe that energy is able to have particulate behavior as well as behaves like a wave, right? So one small packet here represents a photon. And this represents a wave, so or the wavelength between two successive points on a wave. Oh. So the things you need to know about the photon is that it has energy. It is determined by the frequency of the wave. So E, so where this comes again, E is equal to H if V. Frequency is defined as number of waves passing a fixed point per second. Units of per second or hertz. But here, remember the photon is a massless packet. Okay. We have speed. Distance traveled per second. Distance traveled by a wave. So the units is meters per second. Or meters per second, same thing. And finally, the wavelength to the wavelength is the distance between two consecutive points on the wave. two consecutive points on the wave, which is between two troughs or between two crests. So essentially right now, for our purposes here, we are saying that light has a dual nature. It behaves like a wave, and at the same time, which is why it can diffract and spread and all of those things. But it also behaves like a particle. So now we are talking about electrons as well. We speak about when we say the electron is giving off energy, we're saying the electron is giving off a photon of energy. So these are the equations that will be used. E is equal to Planck's constant times frequency, or we can say energy is equal to Planck's constant times speed of light over wavelength. And therefore, we can conclude that frequency is equal to speed over wavelength. And there are some little things to get from this as well that will be relevant. It's a little notation, and then that's it. We can talk about the past papers. Final notation. Guys, I should ask, when you get back the grades, do you get a notification that your grades are ready?
Yes, miss.
It's an email, okay. All right, so also, just letting you know that, okay, good. The other thing is this. So, the first 2 weeks or so you were settling in, right? So we're settling in. So I wasn't really pressuring you just yet, but I want to tell you that hopefully by now you're settled. And when it comes to past paper questions, I am most strict on students who do Unit 1 chemistry. That's when I'm most strict, because we would have been doing it for years and we'd have had so many students, and basically by watching how the student, how many past papers the student did and how the student was scoring in the past papers, it usually correlates very well to how they do in the actual exam, right? So because we are basically having you do the past papers weekly according to the topics that you're learning, and by the time you get to the exams, there would be no topic that you would have not done an exam type question on. And CAPE, even though they're not going to repeat the multiple choice, but they may not repeat the paper too, but they repeat the same concept. So then they're going to ask something that you did already in the exam, in a past paper question. So you have to do the questions. By now, everybody should have sorted out their Canvas accounts. What I find though, guys, when I sent you the Canvas invitation, and you clicked it and you got into the account, but I also sent you a video saying that you need to finish setting up the account with a password and all of that. If you never did that, what's going to end up happening is that when you try going back to use that same email link, it's going to block you out. So please make sure that you set up the Canvas accounts, right? That everybody goes inside, everybody that's in the class. And this is the thing also, if you even miss the class, I'm still expecting the assignment to be done and submitted, because remember, the recordings are added. So what you would need to do is just make time to watch the recording and submit that, right? So I'm still only seeing half of you that are here submitting the classwork, half. 50% of you. So you see the other 50% of you which have not been, you weren't settled, well, that has to end starting this week. All right. Every single person, once you are here, whether or not you're here or not, as I said, you're in the program. You're responsible for the information that we teach every week. So if you weren't here in the live class, then usually by the following day, I'll put up the recording because I have to wait until the recording is processed before I can add it. And you can also, or if you can't wait, you can watch the one that we did last year. So there's always a video. What I do is that I replace the one from last year with this one that we just did by tomorrow. But either way you take it, you're responsible for that information for that week. So it simply means that you may need to watch recording under the question, but at the end of the day, everybody must submit the past papers for Unit 1, especially for K and especially for Unit 1 chemistry. So I'm expecting going forward that we're going to upload. And usually once everybody is settled in, we will check for the classwork, but we'll give you some time and we check. And once you see that you have not made a submission, that's when we start reaching out to the parents and saying, well, we haven't seen the submission yet. We are going to give you one more day to get it in. So just start organizing yourself, guys. I know 6th form is new to you and this was new, so that's giving you some time to get organized and settled. And I think you should be settled by now. All right, so if you have finished copying this, let me just show you what we have for class right now. And and the Zoom code should be here. So if you want to join online, the Zoom code that we'll be using for the rest of the classes will be up here. All right, so we just completed atomic theory and the hydrogen emission spectrum. So now we have the questions to do based on the hydrogen emission spectrum. All right. So here are some past papers. This one is from 2019. The later past papers are 2020. Well, there never was a paper in 2020 because of COVID. But like 2021 going down, I normally, and sometimes I don't normally use them here because I like those kind of being fresh when we get to like the marathons and stuff. But as I said, there's nothing new that they're gonna ask. It's just wording different. So figure 1 shows the wavelengths of the most prominent lines in the visible region of the atomic hydrogen spectrum, right? So they're like, explain how the spectrum is produced. Well, this could be interpreted. I think its interpretation means the procedure. Because this is very vague. How? It could be asking you what the electrons were doing that gave the lines, or it could be the procedure. So I would be on the safe side and I would kind of give a little bit of both. So I would just say that the hydrogen atoms were they were given electrical energy, and the light that was emitted from the hydrogen was analyzed in a prism to give the spectrum. And then that would take your slide probably 2 lines right there. And then I would go on to say, and each line in the spectrum represents a transition that the electron made from a higher quantum level to the n = 2 level. And each color represents a wavelength of light given off, like something like that. So you want to give, for the 3 marks, you want to tell exactly a little bit of the procedure, like you're summarizing the procedure of what they actually did to produce the spectrum. And then you tell really what does each line in the spectrum, what does it mean? All right. So for 3 marks, identify the series. Well, this is the Balmer series because we're seeing the lines. One of these lines, guys, is actually not in this. This is probably ultraviolet. Ultraviolet starts from 400 nanometers or like 390 nanometers up. So one of these lines actually belongs to the ultraviolet spectrum because we know the Balmer series has 4 lines. So then the next thing is, how does the lines in this figure provide evidence for the discrete initial levels of information? So that would come back to the last set of notes, literally, as I wrote it. How does the spectrum provide evidence? So you want to say what I said there. The fact that you are getting discrete specific lines suggests that there are discrete specific energy levels in the atom, right? If it were not so, we would have gotten a continuous spectrum, right? With all possible colors representing all possible transitions. And the fact that we're not getting that suggests that no, the energy levels are fixed, right? So basically what I gave you in the notes, you summarize it here. So in figure 2, draw the electron transitions occurring between the energy levels associated with the origin of the lines in the hydrogen spectrum, right? So, and we did that. So we know that if you go from number 3 to number 2, you get the red line. From number 4 to number 2, you get the cyan. Number 5 to that, you get the blue. And number 6 to number 2, you get the violet. As I said, maybe I would even, from number 7 to number 2, is going to give you ultraviolet. So I believe that this line here, this last line here, represent if you were coming from number 7 to number 2, but it's not in the Balmer series. That's going to be going over into the ultraviolet series, right? Oh, they actually have number 1 there. So maybe, guys, what would have made sense, and now I understand why that line was there. So it simply means that one of them, no, I think the other line was number 7 to number 2. But let me just use this as a teaching point. So sometimes, right, depending on what the electron wants to do, sometimes the electrons go to the number 1 level. So they could go from number 2 to number 1, number 4, 5, whatever. But this is a different series. This series is the Lyman series. So because we can't see this, this is not what the past paper is asking, but I'm just mentioning it to you. If the electron were to have gone back to number 1, the energy being given off would be so great that we would not be able to see it in the visible region. It would be ultraviolet light, and we couldn't see it with our naked eye. So that's the Lyman series. Then no, you have another series, which is where the electrons stop at number 3. So there is this. These should all be coming from the other one. But anyway, I'm just saying it to you, and you'll see it in your notes when you read the notebook. So this is the Pashkin series, and this is in the infrared range. So we can't see infrared, and we can't see ultraviolet. So the electrons are stopping. Some of them are stopping at number 3, and they are giving off infrared, but we can't see that. That's why it wouldn't show up when we look at the Balmer series. And then some of them in the atom do stop at number 1, but we can't see that either because we can't see ultraviolet. What we can see is when they stop at number 2, because then they give off visible light, right? So as I mentioned, guys, remember there are trillions of atoms. So each atom is doing whatever it wants to do. And then when we analyze the sample, we're basically seeing the total of what all these trillions of atoms are doing. But even though we had trillions of atoms of hydrogen in the jar, we only got 4 colors. So it doesn't matter. It means that outside of those 4 colors, they were not doing anything different. All of them, trillions and millions of them, were doing the same thing. So it proved to us that these energy levels are fixed. All right, state the region in the electromagnetic spectrum in which the lines of the Balmer series occur. So this would be the visible region. And then here now, it says calculate the energy of a quantum of radiation with the frequency like this. So basically you'd use the equation E is equal to HV. So they give you the H and they give you the V. So basically you just have to multiply them and find the energy. Yeah, literally. So, and then this last question here was just a remnant of Dalton's, yeah. I think you probably did this already, but you can do it again. 3 of Dalton's atomic theory and 1 that was modified later on, right? So this is what you have based on what we've covered so far, the hydrogen emission spectrum, right? So, so what I did say is omit the last question. So you don't need to do the one about Dalton's atomic theory, because we actually don't factor it in the total number of marks. So you don't have to do it. So it's just the one on the hydrogen emission spectrum that you have to do. All right. So guys, that's where we stop today. Do you have any questions? Any questions on what we completed today?
No, miss.
Yes.
All right. Okay, guys. So review it and remember that you all have to do this work and submit it. You have to start doing that now, right? All right, guys. So enjoy the rest of your day. See you next. Bye, guys.
Goodbye, miss.
Excuse me, miss.
Yes.
I have a question about the Canva. So I signed into with my personal account, and right now I'm seeing Unit 1 biology exams, but I'm not seeing my chemistry.
Okay.
I'm
All
not
right.
sure
So
what to
let
do.
me resend. So you ever got a chemistry one before?
No, I've never gotten a chemistry one.
Okay. All right. So let's just send. We'll send it then.